We will discuss in this video about non-deterministic finite automata, and I'm going to give you in this lecture an intuitive image about what these kind of automata are. And I'm going to follow in the next lecture with a formal definition. So I will start the discussion by reminding you the essence of what deterministic finite automata were. And for them we use sometimes the abbreviation DFA. So I argue that there are essentially two key ingredients in the definition of deterministic finite automata. One of them is that they have to read the input letter by letter. And the other one is that for a state and a letter, the transition to the next state is unique, or we could also say that it's deterministic. And it's really these 2 points that non-deterministic finite automata are changing. In some sense, what non-deterministic finite automata are proposing as a model of computation is more leeway for how the computation is defined, they will take two types of freedoms with their mode of action. So non-deterministic finite automata, structurally they are not that different from the deterministic ones that you have seen in the previous lecture, but they will take they will get rid of these two constraints, and they will have the ability of skipping the moving of the reading head. So this is in as opposed to the way deterministic automata were, that they would read the input letter by letter. So in each reading you would move the reading head. Here in non-deterministic automata, you don't really have to move the reading head. You can just keep it on the same location. And the other freedom they take is for a state and a letter. There may be several transitions. There may be several possible transitions. So if you want, this is the same as saying several possibilities for what the next state may be. And we will see in the next lecture how exactly is this defined. A transition function doesn't do anymore. We will have to have a transition relationship. But the point here is that you are in a state and you are reading a letter from your input tape, and you may have several different options for what the next state may be. And this is all defined in the specification of your non-deterministic finite automata. So right away, as a consequence, what you have obviously is that for an input word, there may be several computations. And this is really a direct consequence of this second freedom that non-deterministic finite automata are taking. Since you have, in a step, you might have several different possibilities for how to change the state. That obviously leads to several, potentially many different computations for a given input word. And so that brings us to the concept of accepting or rejecting an input word. This was a very easy concept in deterministic finite automata. You would have one single computation for that input word, and you would accept the word if and only if the result of that unique computation would bring you to a final state. But here in non-deterministic finite automata, so maybe I'm going to write it also for DFAs, just so that you have it in mirror. So in DFAs, unique computation on the input word u, and you would say u is accepted if the unique computation on u would bring you to a final state, and you would say that u is rejected if this unique computation brings you to anywhere else but the final state. But here we have several different computations, so we will have several computations on input word u, and you will say that u is accepted if there is a computation, at least one, on u ending in a final state. So you would say that this is accepted if there is at least one accepting computation. And you will say that u is rejected, so this is the negation of this condition. So u is rejected if all computations on u end in a non-final state. So we are asking, by negation of that condition, we are asking that we reject the word if all possible computations, however many there may be, all computations, they end in a non-final state. And if you like, the main conceptual difficulty with non-deterministic finite automata is really in this part of the definition, that to check whether a word is rejected or accepted, you might have to check all possible computations in the case it's rejected, or you might have to check really quite many computations until you find one that's accepted. You don't really know which one to check, and in fact you have to check all of them. And I'd like to give you an example now to appreciate even more the advantages in some sense of non-deterministic finite automata. There is a brevity of formulating computations in a non-deterministic world, but also the disadvantages of doing computations in this non-deterministic world. So here is one example. So the example I want to build is, I want to build a non-deterministic finite automaton. So I will say build an automaton, and I'm going to build a non-deterministic one. So build an automaton accepting all binary words having having letter 1 on the third position from the right. So in other words, what I would like to build is really, I would like to build an automaton that accepts all the words such that they have anything here on the last position, anything here, they have to have one on this position, and really anything on this part. So I would like to accept all such words and only such words. And here is how you might think about this in terms of non-deterministic automaton. You might say, well, I have to start reading the input word, and I'm going to start doing that in my initial state. So this is my initial state, and let's just denote this state by P. And in this state, you see, I might have to read quite many letters before I get to the third from the right letter. So really, I stay on this state reading all the letters 0 and 1. And I keep reading until I somehow realize that I am now on position third from the right, in which case I will do something else. So this is, if you like, the waiting state that has to take care of this preliminary part until you reach the third position from the right. And when you may be on the third position on the right, then you are going to switch the state, and that's going to bring you to a new state. So when you reach this third position from the right, you want to read 1. If there is a 1 on that position, then you're going to change state, and then you just check that this was the third from the right. So you just calculate, you do one more transition, and then one more transition here, and this will bring you to your final state. And so again, the logic here is you wait and you keep reading letters from your input until maybe you find a 1 on the third position from the right, and then you check, was this in fact the third position from the right? So you check, I have one more letter to read, and then one more letter, which makes this one the third from the right, and I'm getting here, which is a final state. And I don't even bother specifying further transitions from this state. If there were more letters to be read and I'm in this state, then I'm going to have an undefined computation, which is also allowed in non-deterministic automata. And so the big conceptual difference here with respect to deterministic automata is really in this position P, because you have a transition with 1 that says you stay in state P, which is the same as saying, I don't think that the position I'm reading from the input is the third from the right. So I keep waiting. But also you have a transition with 1 saying, well, I believe that the position I'm reading now is the third from the right. And so you have two possibilities in state P when reading 1. One possibility is you change the state to P, and the other possibility is you change it to Q. And you don't really know which one should be taken, so you would have to check all different possibilities. And a computation on an input word might go something like this. Let's say that you have here your input tape. And I'm not even going to specify, the full content of the tape, but rather I'm going to read it in the same way that the automaton is reading, one by one. And let's say I have, the first position on the input is letter 1. So what the automaton is doing is it's starting in state P, and it checks. So in state P with transition 1, I have two possibilities. One, I stay in P, and the other one, I stay in Q. And this is the same thing as guessing whether your input word has length 3, meaning this one is third from the right, or it doesn't have length 3. So, and you have no way of knowing just by reading this one, because you cannot really look ahead to see the length of your word. And so in state P, just reading this letter 1, there are two different computations your automaton may do, and I'm going to indicate them in this way in here with a branching tree of computation. So one possibility is I stay in state P, which is the same as saying I take this transition. The other one is I will take this transition. And now we have two possible computations that we would have to check in order to see whether at the end of reading our input word we are in a final state or not. And then you move your head, your reading head, and you are on this position. And let's say that on this position you see letter 1. And again, reading letter 1, I check this part of the computation. So just like before, being in state P and reading letter 1 gives me two possibilities for my computation. One is I stay on state P, and the other one is I stay I move to state Q. And if you like, again, this is the same. So going on that branch or going on this branch is the same as saying I believe that this is the third from the right, meaning I believe that my input word is of length 4, that's this branch, or saying, no, I don't think so, and I keep waiting. That's not the one that I was waiting for. It's just another one. It's maybe one of these preliminary ones. And for this branch of the computation tree, when you are in state Q and you read 1, there is only one possible transition. And this really, I mean, you have made a guess that this was the third from the right, and now you're just counting to see that whether your guess was correct or not. And let's say that you are now moving your reading head, and let's say that on this cell you find letter 0. And again, I have to check all these 3 possible computation trees, and being in state P with 0, I stay on P. And being in state Q with 0, I move to state R. And being in R with 0, I move to state S. And then you move your reading head, and let's say that on this position you found letter 1. And again, in letter 1, I have to check all of these, all these 3 computation trees. And just like before, in state P with letter 1, I have 2 possibilities for my computation. One is you stay in state P, and the other one is you switch to state Q. In state R, there is only one possibility. You go to state S with 1. And here in state S, in fact, there is not even a transition defined. So this computation is clearly not continuing. So it's not a successful computation. It's not an accepting computation. And let's say that this is the end of your word. There is nothing else. So you got now to the end of your computation. And now you are checking. So this state, so for this computation path, this is one computation, you got at the end, and this is not a final state. P is not a final state. And for this computation tree, you got into state Q, and this is also not a final state. And for this one, in fact, you couldn't even compute to the end, and obviously that's not an accepting path either. But as it turns out, this path is an accepting path. So that got you to a final state. So the conclusion is that 1101 is accepted. And you can check that this is correct. It should be accepted because, in fact, I do have 1 on the third position from the right. So this is the diversity of computations you might have in non-deterministic automata. Some of them rejecting, some of them accepting, and to accept the word, it's enough to have at least 1. Even a single accepting computation is enough to declare this word accepted. So there is in fact a deep level in this notion of non-determinism that I would like to draw your attention to. And in fact, this leads to some of the most interesting concepts in computer science that you might see in other courses. So I'm just opening the door in this course to things that you might see later on in your studies. And what I would like to draw your attention to is that even though it's tempting to think about these multiple possibilities you have for your computations, even though it's tempting to think about them in terms of probabilities, in terms of having several different choices and maybe choosing some of them, this is not the same. So non-deterministic computation is not the same as probabilistic computation. And I want to draw your attention to this because in some sense I find the concept of probabilistic computation, at least on on an intuitive level, maybe easier to grasp than the non-deterministic one. So I find that this comparison is often useful. So if you think just on an intuitive level, I'm not defining here probabilistic computations, but just on an intuitive level, you have this idea that all computation paths are possible. But some of them are more likely than others. So you have some, probability distributions, and I don't go into that jungle. So, but some of them more likely than others. And it's really, I mean, very often in probabilistic computations, it's just enough to explore more likely computation paths to give the answer with high enough probability, to give D or to give an answer with high enough probability. And I just want to draw your attention that this is completely different, not at all the same. So they're extremely different notions, even though this one might be more tempting to imagine as an intuitive model of computation. But this one, in fact, is nothing like this. So obviously, I mean, you have all computation paths possible. So all of them have to be explored. All computation paths are possible. All computation paths lead to some answer whether it's accept or reject, but they all lead to some answer. And we don't know a priori if there are any accepting computations. And that's the big problem with this model, because we don't know a priori. We have to explore all of them. So we don't know if there are any accepting computations. So that means that we must explore all of them. And so this is something that I would like you to understand as a concept from the very beginning. In non-deterministic computations, you've got to explore all of them, at least until you find one accepting computation. And if you keep rejecting computations, you have to explore all of them until you convince yourself that all of them are rejecting, or until you find one that's accepting. And then you declare your word, depending on which case you were in, as accepted or rejected. In the next video, we are going to make this notion more concrete, and I'm going to give the mathematical definitions for what a non-deterministic automaton is and what a non-deterministic computation is. But I think that this intuition should help you when we go to these definitions. One thing that I still want to add on this intuitive level is that this notion of non-determinism is in fact an extremely powerful way. Maybe I'm even writing this. So this is a powerful way to deal with incomplete information. And the example I had on the previous whiteboard was in fact suggestive of this case. I wasn't quite sure when I was reading the input tape whether I was or not on the third position from the right, because I couldn't look ahead. So and still I could manage it with a relatively small non-deterministic finite automaton. So this sort of non-deterministic devices, they represent a powerful way to deal with incomplete information. The other thing is that the notion of non-determinism leads to perhaps the most famous problem currently open in theoretical computer science. And it's not necessarily in the context of finite automata, it's in a slightly broader context, but it leads to this very famous problem that I'm going to write here in this form, whether the world of deterministic polynomial time computations is the same or not as the world of non-deterministic polynomial time computations. This will be discussed in some other courses.